Hello everyone. Today we are going to analyze this beam using stiffness matrix method. Before analyzing, let's see the beam one time. In this beam, there are three spans: span AB, span BC, and span CD. In the span AB, there is a point load 20 kN acting on the center. In the span BC, there is a point load 25 kN acting at 2 meter from the support B. In the span CD, we are having UDL 12 kN per meter acting for the full span. In the point A and in the point D, there are fixed supports. In the point B and in the point C, there are hinged supports. The moment of inertia for the span AB is 2I. For the span BC, it is 1.5I. For the span CD, it is 0.8I. Span AB is 4 meter long, span BC is 5 meter long, and the span CD is 4 meter long. In this beam, we have to calculate 6 moments. In the fixed support, there will be a moment. So in the point A and in the point D, we are having moments. In the point A, we are having the moment MAB, and in the point D, we are having the moment MDC. In the joints, there will be two moments. In the joint B, we are having two moments MBA and MBC. Also, in the joint C, we are having two moments MCB and MCD. So, totally, we have to find 6 moments. Also, we have to calculate 4 vertical reactions RA, RB, RC, and RD. Now, let us make the fixed end moments. For making the fixed end moments, we have to assume every span as a separate fixed beam. First, let us take the span AB and assume that it is a separate fixed beam. Now, let's see the formulas to calculate the fixed end moments. In this table, you can see some of the important fixed end moment formulas for the different type of loadings. In the span AB, there is a point load acting on the center. So we have to select this condition. The formulas are minus WL upon 8 and positive WL upon 8. In the span BC, there is a point load. That point load is not acting on the center. So we have to select this condition. The formulas are minus WAB square upon L square and positive WA square B upon L square. In the span CD, we are having UDL acting for the full span. So we have to select this condition. The formulas are minus WL square upon 12 and positive WL square upon 12. Now let us apply those formulas and find out the fixed end moments. In the span AB, we are having a point load. This point load is acting in the center. We have already seen the fixed end moment formulas minus WL upon 8 and positive WL upon 8. MFAB will be negative because it is acting in the anticlockwise direction. MFAB will be positive because it is acting in the clockwise direction. Let us apply the values inside the formulas. W is 20, L is 4. After calculations, we are getting MFAB is equal to minus 10 kN meter and MFBA is equal to 10 kN meter. Now let us calculate the fixed end moments in the span BC. In the span BC, there is a point load. This point load is not acting on the center. We already saw the formulas for the fixed end moments minus WAB square upon L square and positive WA square B upon L square. Let us apply the values inside the formulas. W is 25, A is 2, B is 3, L is 5. After calculations, we are getting M of BC is equal to minus 18 kN meter and M of CB is equal to 12 kN meter. Now let us make the fixed end moments in the span CD. In the span CD, we are having UDL acting for the full span. We already saw the formulas for the fixed end moments minus WL square upon 12 and positive WL square upon 12. Let's apply the values inside the formulas. W is 12 and L is 4. After the calculations, we are getting M of CD is equal to minus 16 kN meter and M of BC is equal to 16 kN meter. In the stiffness matrix method, we have to check the number of supports in which slope can occur. Let us see the conditions. In the fixed support, there will be no slope. In the hinged support, there will be slope. Also, in the roller support, there will be slope. In this beam, in the points B and C, we are having hinged supports. So, the number of supports where slope occurs is 2. In the point B, we are having theta B, and in the point C, we are having theta C. So, in this analysis, there are two unknowns. If we calculate these two unknowns, we can easily find the final moments. Now, let us make the fully restrained structure. In the fully restrained structure, there will be no slope. We already know only in the fixed support there will be no slope. So let us remove the hinged supports from the point B and from the point C and replace them with the fixed supports. Right now in this beam there is no slope because all the supports are fixed. That is why it is called the fully restrained structure. We have made the fully restrained structure. Now let us make the coordinates diagram. In this analysis, there are two coordinates. In the point B and in the point C, we are having the coordinates because in these points only we are having slope. The coordinates should be made in the clockwise direction. You can see that both of the coordinates are made in the clockwise direction. Now let's see the formula to calculate the slope values. System displacement delta matrix is equal to K matrix inverse into P matrix minus PL matrix, where PL matrix is the moments developed in the coordinates due to the given load. P matrix is the final forces acting in the coordinate direction. K matrix is the stiffness matrix. In this formula, first let us calculate PL matrix. We know that PL matrix is the moments developed in the coordinates due to the given load. In this analysis, we are having two coordinates. In the point B and in the point C, we are having the coordinates. In the point B, we have calculated two fixed end moments, M of BA and M of BC. Let us add them. After adding, we are getting minus 8. In the point C also, we have calculated two fixed end moments, M of CB and M of CD. Let us add them. After adding, we are getting minus 4. In this analysis, there are two coordinates. So, inside the PL matrix, we will have two values. First value from the first coordinate and the second value from the second coordinate. In this formula, now let us calculate the P matrix. If in the beam there is overhanging, we have to calculate P matrix. Otherwise, we can simply enter 0. In the given beam, there is no overhanging. So we are just entering 0, 0. Inside the P matrix also, we will have two values because we are having two coordinates. But both of the values are 0 because in this beam there is no overhanging. In this formula, now let us calculate the stiffness matrix. Now let's see how to calculate the stiffness. For calculating the stiffness, we have to apply the unit displacement, that is theta is equal to 1 radian in every coordinate. In this analysis, we are having two coordinates in the point B and in the point C. So in these points, we have to apply the unit displacement. Then we have to use the formulas. If the fair end is fixed, the formula is 4EI upon L. If the fair end is hinged, the formula is 2EI upon L. We have to be very careful. We have to apply the unit displacement in the fully restrained structure, not in the given beam. Now let's see the size of the stiffness matrix. For 3 coordinates, the size will be 3 by 3. For 2 coordinates, it will be 2 by 2. For 1 coordinate, it will be 1 by 1. In this analysis, we are having 2 coordinates. For 2 coordinates, the size will be 2 by 2. Inside the matrix, we will have 2 rows and 2 columns. In this matrix, first let us calculate the first row. For that, we have to apply the unit displacement in the first coordinate. Let us apply the unit displacement in the first coordinate, that is in the point B. In the point B, we are having fixed support, but when we apply the unit displacement, it is no longer a fixed support. It becomes a hinged support because in the fixed support, there will be no displacement, but we have applied the unit displacement, so it becomes a hinged support. Now let's see how to draw this curve. We are applying unit displacement in the point B. The point B is the joint. It is connecting two spans BA and BC. So in the point B, we have to make two clockwise curves, one towards the point A and one towards the point C, but both of them should be in clockwise direction. Then we have to see the direction of the arrows in both of the curves. This arrow indicates upwards, so the curve comes above the span. This curve indicates downwards, so the curve comes below the span. In the fixed supports, there will be no slope. In the point A and in the point C, there are fixed supports. So we have to give some gap between the fixed supports and the curves. You can see that I have given some gap between the fixed supports and the slope curve. Now let us calculate the stiffness values. The stiffness values should be calculated in the order, first from the first coordinate, then from the second coordinate. K11 we have to calculate from the first coordinate. K12 we have to calculate from the second coordinate. In the coordinates diagram, we have made the coordinates in the clockwise direction. In the same way, we have to make K11 and K12 in the clockwise direction. Now let us calculate K11. For that, from the point B, we have to look on both the sides. On the left side, we are having fixed support. If the fair end is fixed, the formula for the stiffness is 4EI upon L. Here, the moment of inertia is 2I. So, inside the formula, instead of I, we have to apply 2I. Length of AB is 4 meter. Let us apply that. Now, let us look on the right of B. On the right of B also, we are having a fixed support. So, we have to apply the same formula 4EI upon L. For BC, the moment of inertia is 1.5I. The length of BC is 5 meter. For K11, we are having two values. We have to add both of them. After adding, we are getting 3.2 EI. Now let us calculate K12. For that, from the point C, we have to look on both the sides. On the right side, there is no slope curve. If there is no curve, there will be no stiffness value. On the left side, we are having hinged support. If the fair end is hinged, the formula for stiffness is 2EI upon L. For CB, the moment of inertia is 1.5I, length is 5 meter. Let us apply both of the values. Finally, for K12, we are getting 0.6 EI. Now, let us calculate the second row in the stiffness matrix. For that, we have to apply the unit displacement in the second coordinate, that is in the point C. In the point C, we are having a fixed support, but when we apply unit displacement, it is no longer a fixed support, it becomes a hinged support. Now, let's see how to draw this curve. From the point C, we have to make two clockwise curves, one towards the point B, one towards the point D. Both of the curves should be in the clockwise direction. Then we have to see the direction of the arrows. This arrow indicates upwards, so the curve comes above the span. This curve indicates downwards, so the curve comes below the span. We already know we must give some gap between the curve and the fixed supports. You can see that I have given some gap between the fixed supports and the slope curve, because in the fixed supports there will be no slope. That is why the curve ends before the point B and can't continue after the point B. Now let us calculate the stiffness values. We know that the stiffness values should be calculated in the order, first from the first coordinate, then from the second coordinate. Let us calculate K21. For that, from the point B, we have to look on both the sides. On the left side, there is no slope curve. If there is no slope curve, there will be no stiffness value. Now let us look on the right of B. On the right of B, we are having a hinged support. If the fair end is hinged, the formula is 2EI upon L. For BC, the moment of inertia is 1.5I. So instead of I, we have to apply 1.5I. Length of BC is 5 meter. Let us apply that. Finally, for K21, we are getting 0.6 EI. Now, let us calculate K22. For that, from the point C, we have to look on both the sides. On the left side, we are having a fixed support. If the fair end is fixed, the formula is 4EI upon L. For CB, the moment of inertia is 1.5I and length is 5 meter. Let us apply that. Now let us look on the right of C. On the right of C also we are having a fixed support. So we have to apply the same formula 4EI upon L. For CD, the moment of inertia is 0.8I, length is 4 meter. Let us apply the values. For K22, we are having two stiffness values. We have to add both of them. After adding, we are getting 2EI. In the stiffness matrix, we have calculated both of the rows. Let us apply them. EI is constant for all of the values, so let us take it outside. In the system displacement formula, we have calculated everything. Let us apply the values. EI inverse is equal to 1 upon EI. Then we have to add these two matrices. After adding, we are getting this. For this matrix, we have to calculate the inverse. We can apply all of the values inside the calculator and get the inverse. If you do not know how to calculate inverse in a calculator, see the description below. There is a link. You can click the link and watch the video. I have used the calculator and got the inverse. Then we have to multiply these two matrices. You can see the multiplication here. Finally, we are getting the answers. We know that in this analysis, the system displacements are the slopes, which we got finally. The slope values will be according to the coordinates. The first coordinate is the point B, so first we will get theta B. The second coordinate is the point C, so here we will get theta C. In this analysis, we have calculated both of the unknowns. Now let us make slope deflection equations and find the final moments. First, let us make the slope deflection equations in the span AB. Here, let us apply the fixed end moments. We have already calculated the fixed end moments. In the point A, we are having a fixed support. In the fixed support, there will be no slope. So, theta A will be 0. For AB, the moment of inertia is 2I and the length is 4 meter. Let us apply in both of the equations. After applying the value of theta B in both of the equations, we are getting MAB and MBA. Now let us make the slope deflection equations in the span BC. In the span BC, moment of inertia is 1.5I and length is 5 meter. Let us apply in both of the equations. After applying the value of theta B and theta C, we are getting MBC and MCB. Now let us make the slope deflection equations in the span CD. In the span CD, moment of inertia is 0.8I and length is 4 meter. Let us apply in both of the equations. In the point D, we are having a fixed support. In the fixed support, there will be no slope, so theta D will be 0. After applying the value of theta C in both of the equations, we are getting MCD and MDC. In this analysis, we have calculated all of the moments. For MAB, we are getting a negative value. That means MAB is acting in the anticlockwise direction. In the point B, we are having two moments. For MBA, we are getting positive value because it is acting in the clockwise direction. For MBC, we are getting negative value because it is acting in the anticlockwise direction. In the point C also, we are having two moments. For MCB, we are getting a positive value because it is acting in the clockwise direction. For MCD, we are getting a negative value because it is acting in the anticlockwise direction. Finally, for MDC, we are getting a positive value because it is acting in the clockwise direction. Now, let us calculate the reactions. First, let us take the span AB and calculate the reactions. In the span AB, there are two moments, MAB, which is acting in the anticlockwise direction, and MBA, which is acting in the clockwise direction. In this span, first I am going to calculate RA. For that, I am going to take moment about B. In this case, I am moving towards right hand side. Clockwise will be positive and anticlockwise will be negative. The vertical reaction RA is acting towards the point B in the clockwise direction, so it is positive and the distance is 4 meter, so 4 RA. The point load 20 kN is acting towards the point B in the anticlockwise direction, so it will be negative and the distance is 2 meter, so 20 into 2. Then there are two moments. 7.75 moment is acting in the anticlockwise direction, so it will be negative. 14.5 moment is acting in the clockwise direction, so it will be positive. Finally, for RA, we are getting 8.31 kN. Now, using the rule, summation of vertical forces is equal to 0, we can calculate RV1. In this span, there are three forces. RA and RB1 are acting upwards, so both are positive. Point load 20 kN is acting downwards, so it is negative. We already know the value of RA. Let us apply that. In this way, we can get RB1, which is equal to 11.69 kN. Now, let us calculate the reactions in the span BC. In the span BC, there are two movements, MBC, which is acting in the anticlockwise direction, and MCB, which is acting in the clockwise direction. In this span, first I am going to calculate RB2. For that, I am going to take moment about C. The vertical reaction RB2 is acting towards the point C in the clockwise direction, so it will be positive and the distance is 5. So 5 RB2. The point load 25 kN is acting towards the point C in the anticlockwise direction, so it will be negative and the distance is 3 meter. So minus 25 into 3. Then we are having two movements. 14.5 is acting in the anticlockwise direction, so it will be negative. 14.94 is acting in the clockwise direction, so it will be positive. Finally, we are getting RB2 is equal to 14.91 kN. By applying the rule, summation of vertical forces is equal to 0, we can calculate RC1, which is equal to 10.09 kN. Now, let us calculate the reactions in the span CD. In the span CD, there are two movements, MCD, which is acting in the anticlockwise direction, and MDC, which is acting in the clockwise direction. In this span, first I am going to calculate RC2. For that, I am going to take moment about D. The vertical reaction RC2 is acting towards the point D in the clockwise direction, so it will be positive and the distance is 4 meter, so 4 RC2. The UDL 12 kN per meter is acting in the anticlockwise direction towards the point D, so it will be negative and the distance is 4 meter. When the UDL comes, we have to multiply with the distance and the distance by 2. So 4 into 4 by 2. Then we are having two movements. 14.94 is acting in the anticlockwise direction, so it will be negative. 16.53 is acting in the clockwise direction, so it will be positive. Finally, we are getting RC2, which is equal to 23.6 kN. Using the rule, summation of vertical forces is equal to 0, we can calculate RD, which is equal to 24.4 kN. Now, let us add RB1 and RB2. After adding, we are getting RB, which is equal to 26.6 kN. Also, let us add RC1 and RC2. After adding, we are getting RC, which is equal to 33.69 kN. Now, we are going to draw the shear force diagram. I am going to calculate the shear force values from the point A and towards the point D. In this case, I am moving towards right hand side. Upwards will be positive and downwards will be negative. You can see the shear force values. Using the values, we can draw the diagram. Now, we are going to draw the bending moment diagram. For drawing the bending moment diagram, first we have to make the free moment diagram, then end moment diagram. Finally, we have to combine both of them to get the bending moment diagram. For the free moment diagram, we have to assume every span as a separated simply supported beam. First, let us take the span AB. In the span AB, a point load 20 kN is acting on the center. If a point load is acting on the center, the bending moment formula in the simply supported beam is WL upon 4. Here W is 20, L is 4. When we apply inside the formula, we are getting 20 kN meter. In the simply supported beam, if the point load is not acting on the center, the formula to calculate the maximum bending moment is WAB upon L. Here W is 25, A is 2, B is 3, L is 5. When we apply inside the formula, we are getting 30 kN meter. In the simply supported beam, if the UDL is acting for the full span, the formula to calculate maximum bending moment is WL square upon 8. Here W is 12, L is 4. When we apply inside the formula, we are getting 24 kilonewton meter. Using these three values, we can draw the free moment diagram. Now let's see how to draw end moment diagram. For drawing the end moment diagram, we have to see the direction of the curves. First, we have to arrange these movements in the curves. For MAB, we are having a negative value because it is acting in the anti-clockwise direction. So, in the point A, we have to make an anti-clockwise curve towards the point B. For MBA, we have a positive value. That means it is acting in the clockwise direction. So, from the point B towards the point A, we have to make a clockwise curve. For MBC, we are having negative value. That means it is acting in the anti-clockwise direction. So, from the point B towards the point C, we have to make an anti-clockwise curve. In the same way, we have to make the curves in the point C and in the point D. Then we have to see the direction of the curves. All of the curves are indicating upwards. That means the end moment diagram comes above this line. Finally, we can connect the values and make the end moment diagram. If the end moment diagram comes below this line, that will be positive. If it comes above the line, that will be negative. Right now, all of the points are coming above this line, so it is negative. Now, let us combine the free movement diagram and end movement diagram and make a bending moment diagram. Here you can see that I have combined both of the diagrams. If you are very experienced, there is no need to make the end movement diagram and free movement diagram. We can directly make the bending moment diagram. Wherever the free movement diagram and end movement diagram are alone without mingling with each other, we can mark the values. Here the end movement diagram, here free movement diagram, end movement diagram, free movement diagram, end movement diagram, free movement diagram, finally end movement diagram. Wherever they are together, we are not marking anything, we just keep the space empty. Now we are going to end this session. Thank you for watching this video.